Hello everyone, this is Xingyao. It's my honor to present our work, PerSiVal, on body AR visualization of biomechanical arm simulations, a collaboration with David, Johannes, Benjamin, Frank, Christian, Oliver, and Michael. This is a 5-year-long story which was accepted by IEEE Computer Graphics and Applications. As you may have already known, biomechanical simulation analyzes and predicts human movement mechanics. Biomechanical simulation has widespread applications, for instance, in sports science to optimize performance and prevent injuries, in biomechanical engineering when designing prosthetics, or in rehabilitation medicine to enhance related outcomes. However, simulating the human body was quite complex, which means that it had to rely on high-performance computing setups, and hence was limited to professional scenarios where it was used by, for instance, researchers, doctors, and physiotherapists. A twist happened in 2018. Real-time optimization of arm muscle activation became feasible, enabling fast 3D biomechanical simulations. However, interpreting the simulation outputs still required substantial biomechanical expertise, which limited their accessibility to non-experts. Therefore, we explore bringing biomechanical visualization into more pervasive, everyday contexts. Specifically, we leverage situated visualization with augmented reality to present simulation outcomes where the physical referent is the moving human arm. We brought together expertise in biomechanical simulation, distributed system, and visualization to start the project PerSiVal, with the goal of making biomechanical simulation and visualization available to anyone, anytime, and anywhere. We propose a pipeline to run the complete biomechanical simulation and visualization fully on AR device. First, the motion capture system provides the subject's movement data as input for the biomechanical simulation, which then computes muscle activation levels and muscle geometry. This process can be optimized using distributed processing to reduce computational load. The simulation results are then encoded into a visualization and rendered onto a virtual arm representation. The optimal arm representation is the geometry generated from the simulation process. However, during the early exploratory phase, we also used a pre-existing static arm model as a temporary substitute. Finally, the arm representation, along with the visualization, is projected back onto the subject's arm. To make the final system usable, we propose the 6 design goals. On-body AR, which is our ultimate goal. Virtual arm representation functions as a central medium for visualizing other data. High level of realism was proposed by biomechanical researchers, which showed the detail of simulation results. Motion capture, the basis of our workflow. Pervasiveness means people can use it anywhere and anytime, which implicitly suggests a high level of system integration and portability. Lastly, we want to ensure that the visualization can even be understood by the non-expert. To achieve these goals, we then identified 5 key choices of our system design: motion capture, perspective, AR display, data encoding, and arm representation. We developed 6 prototypes. For prototype 1, we used the Vuforia markers to track the arm movements and HoloLens 1 as the display. The muscle activation levels were encoded into the color of the corresponding muscles. For prototype 2, we upgraded the tracking method to AR Toolkit and the display to HoloLens 2. In the third prototype, we used Outdoor Kinect and the Big TV to form a magic mirror setup, and the muscle activation here were also presented in bar charts and line charts. To reduce visual clutter and help users focus more on the visualization, we use the diminished reality to remove the real arm from the live streaming. We designed prototype 4 for physiotherapists. Here the patient's arm movements were captured by the large-scale mocap system OptiTrack, while the physiotherapy looked at the patient's arm with visualizations. Here the arm angles were visualized around the patient and the bar charts and line charts were on a floating UI panel. When it came to prototype 5, the establishment of the iPad Pro with LiDAR sensor and M1 chip make it possible to run motion capture, biomechanical simulation, and visualization in one mobile device. So we dynamically render the arm geometry based on the simulation, which looked much more realistic. For prototype 6, we had more muscles, and we designed particle visualization to reduce computing cost and the terrifying feeling about raw flesh. Over the past 5 years, we collected feedback from over 70 participants in outreach activities, demos, and discussions. After all, we found that the final prototype met all design goals, and now we are going to reflect our lessons learned in terms of our design choices. First, for motion capture. The marker-based method was easy to deploy but caused frequent tracking loss. The large-scale system, OptiTrack, was the most accurate but jittery with crowded trackers. The depth sensor offers wearable-free experience, but it cannot ensure accuracy when too many people in the same view. In a word, there is always a trade-off between accuracy, comfort, pervasiveness, and time latency. For display and perspective, we attempted to use AR head-mounted display for first-person perspective. However, its limited field of view even didn't allow people to see their own upper arms, so we could only use it for third-person perspective. People found mirror perspective familiar and intuitive to use, as it resembles how people naturally observe and adjust their posture in everyday situations. As for the tablet PC, the iPad Pro offered a highly integrated solution. However, it occupied one of the doctor's hands, making it less useful for physiotherapy scenario, where doctors need both hands to guide the patient's arm. As for arm representation, although the biomechanical researchers require highly realistic rendering of the muscles, the non-experts found it very terrifying, like raw flesh. For data encoding, it was easier for people to notice the muscle color change on the body compared to the diagrams shaped near the body. Finally, we acknowledge several limitations in this study. First, the number of muscles involved is limited, and the patient pool lacks diversity. Second, the simulation process is based on a general model and does not yet support personalized modeling for individual users. In the future, we aim to incorporate a broader range of muscles and a more diverse user population, and to further develop personalized muscle simulations tailored to individual characteristics with the methods such as ultrasound measurements. To conclude our work, we completed a 5-year project about visualizing data on the body. We developed 6 prototypes with different design choices on motion capture, display, perspective, arm representation, and data encoding. We summarized the lessons learned based on the feedback from over 70 participants. And we do hope that this work will ultimately enhance body awareness, reduce cognitive load, result in effective motor training, and better body-centric interaction in the big XR community. Feel free to contact us. Thank you.